Welcome to the Longevity Papers podcast.
Our mission today is a critical assessment of the 5 most impactful papers from this week, November 10th through the 14th, 2025.
And we're focusing squarely on novelty. We're looking for the research that genuinely demands a change in how biotech researchers think and how they invest.
We should probably say this right at the top.
What's that?
This was, frankly, a weak week overall. We went through 69 papers, and most of them were just incremental.
Right, just fitting known puzzle pieces into the established hallmarks of aging.
Exactly. But the 5 we selected, they're different. They represent genuine conceptual breakthroughs.
Absolutely. Our criteria were really strict. Novel mechanisms from high-caliber institutions and with clear pathways to therapeutic translation.
So today, you're getting a rapid-fire tour across 4 critical hallmarks.
We'll cover a really exciting circular RNA telomerase activator, then 2 hyperspecific epigenetic regulators.
A mitochondrial compound that's already in clinical trials, and a highly scalable xenomorphic agent that comes from your own gut microbiome.
The potential is huge, but we have to be honest about the risks, too.
Definitely. Let's start with a hallmark that's always been a bit of a double-edged sword: telomere attrition.
Okay, let's unpack this one. This comes from Yumeng Cui, Yingying He, Zhaoji Wu, and their colleagues at the Laboratory of Advanced Biotechnology in Beijing. They published it on November 12th in Science Advances.
And what's so fascinating here is the molecule itself. Circurs-1. It's a circular RNA, a circRNA.
And circRNAs are known for being much more stable than, say, linear mRNAs. They're resistant to degradation.
Which makes them really promising as therapeutics. So they found that Circurs-1 naturally declines with age, and its job is to act as an endogenous or internal regulator of TERT transcription.
Okay, and this is where it gets really interesting, especially when you compare it to all the past failures in this space.
It's all about the mechanism. This circRNA binds directly to the TERT promoter region.
So the DNA sequence that controls when the telomerase enzyme is actually made.
Precisely. It acts as a cofactor, essentially a molecular handshake. It facilitates the recruitment of RNA polymerase 27 and the transcription factor CFOS.
And when that handshake happens, TERT expression just ramps up.
Right. It's like you're restoring a natural internal throttle, not just flooding the engine.
Which is a huge contrast to the previous attempts. I'm thinking of the small molecule agonists like TA65 or BBR1332.
Oh, yeah, those are just broad approaches. They basically dump fuel on the fire.
And they struggled in safety trials because of it. Too much risk of driving uncontrolled cell growth and cancer.
Exactly. The historical failure was a lack of specificity. But since Circurs-1 is an endogenous regulator that just decreases with age, restoring it might be a much safer, more physiological approach.
And they showed it worked, right, using clinically translatable delivery systems.
It did. Using AAV vectors or extracellular vesicles, they showed systemic rejuvenation improved cognitive function, better physical performance, reduced inflammation.
AAV delivery is great for specificity, but it also comes with huge costs and manufacturing headaches. And are extracellular vesicles truly scalable for a whole aging population? That's a practical hurdle.
That's the question. And on the safety side, we cannot just ignore the risk. Telomere extension is a powerful predictor of lifespan, but that cancer risk still looms large.
So the critical experiments are pretty clear.
Absolutely. Long-term cancer surveillance, full lifespan studies in mice. You have to prove that restoring this natural regulator doesn't push cells over that oncogenic threshold.
Okay, so that's a brilliant specificity win in the telomere hallmark. Speaking of specificity, let's pivot to epigenetic alteration. We saw another huge step forward there.
We did. This next paper is a fantastic piece of work from Karanpour, Ngubo, Stanford, and their team at the University of Alberta. It was published November 7th on bioRxiv.
That's BIORXIV, pronounced bioRxiv. And they focused on Hutchinson-Gilford progeria syndrome, HGPS.
Right, the accelerated aging disorder. Patients typically die in their early teens from vascular problems, and their cells are known for losing this protective epigenetic mark, H4K16 acetylation.
Or H4K16X. It's crucial for stabilizing your chromatin structure for DNA repair.
And for years, all the attention has been on the sirtuin family, specifically ARRT1, as the enzyme that strips off that vital mark.
But that's not what they found. This is the big surprise.
Not at all. Their systematic screens show that HDAC2 is the dominant class I histone deacetylase, responsible for that H4K16 loss in HGPS vascular smooth muscle cells.
Wow. And they checked the highly homologous HDAC1.
They did. Knocking it down had no effect whatsoever.
So this is a crucial mechanistic distinction. It means selective pharmacological inhibition of HDAC2 could work.
Exactly. It could work where the non-specific pan-HDAC-AC inhibitors have failed in the clinic because of toxicity. And they showed it in the cell-selective HDAC2 inhibition restored H4K16 ag and rescued the premature aging phenotypes.
So if you think bigger picture, you have HGPS patients whose lives are cut short by this specific epigenetic error. A modest lifespan extension for them would be a crucial proof of concept for targeted epigenetic fixes in the broader aging population.
And if we link this back to our first paper for a second,
Good.
if Circus-1 is fixing the frayed ends of the DNA, the telomeres, and this HDAC2 correction is fixing the stability of the DNA structure itself.
You're addressing two fundamental layers of genomic decay at the same time.
That's the power of thinking about combination therapy.
Okay, speaking of the vascular system and targeted epigenetics, our third paper gives us a completely new system-wide driver for this.
This is the study by Ruifeng Gao and his colleagues from Zhejiang University, published November 14th in Advanced Science. And they present really compelling evidence that endothelial cell aging is actually causative of systemic aging.
Not just a bystander or a symptom.
No, that's a huge conceptual shift. This has been debated for years, and this paper gives us a specific pathway.
So what did they do?
They engineered mice with an endothelial-specific deficiency in a gene called KDM5A. And those mice had shortened lifespans and a whole host of senescent phenotypes.
And it wasn't just vascular problems.
Not at all. They saw severe fat accumulation, skeletal kyphosis, that age-related hunching, and reduced thermogenesis. It shows that vascular epigenetic drift drives major systemic metabolic breakdown.
So what's the specific mechanism, the KDM5A FAPP4 axis?
Right.
Okay.
KDM5A is a histone demethylase. When they lost it, they saw an increase in H3K4ME3 enrichment at the promoter for fatty acid binding protein 4, or FABP4.
And that specific change drove aggressive FABP4 transcription,
leading directly to the systemic lipid metabolism disorders they observed.
That level of mechanistic specificity is gold for biotech. It identifies a single pathway where we could intervene.
It does, and it raises a key actionable question for anyone in drug discovery.
Are there existing KDM5A inhibitors out there?
Exactly. Small molecules that could be quickly repurposed. This finding gives you a clear mechanistic endpoint to screen for, reversing that epigenetic mark and suppressing FABP4. It's a rapid path to translation.
And rapid translation brings us very nicely to our fourth paper, which deals with mitochondrial dysfunction using a compound that's already in human testing.
This is the study from Arjun Janakula and Benjamin Harrison's group at the University of Washington. It's published to JR Science on the 14th. They looked at the mitochondria-targeted peptide, elamipretide.
Also known as SS31.
That's the one. And it's already deep into phase 2 trials for things like Friedreich's ataxia and heart failure.
Which means you could bypass a decade of initial safety testing for repurposing. I mean, that is the dream scenario for a biotech investor.
It really is. And the mechanism is fundamental. SS31 stabilizes cardiolipin, which is this essential phospholipid in the inner mitochondrial membrane.
And they showed it restored function.
They did.
Yeah.
SS31 treatment restored complex 2-linked respiration in aged mice back to the levels you'd see in young animals.
So that's true functional restoration. And the effect on the aorta was pretty impressive.
Very impressive. Just 8 weeks of treatment reversed age-related aortic aging. We're talking reduced stiffness, less inflammatory MMP9 expression, and better elastin integrity. It's strong evidence of a pharmacological rescue.
But there's always a but.
Of course.
Yeah.
You have to be critical.
Yeah.
The intervention was only 8 weeks in mice. We have no idea if this extends long-term lifespan.
And the delivery method.
Right. Intravenous infusion.
Yeah.
That's a practical limitation. For chronic use in a huge aging population, you need an effective oral delivery formulation. And that's still a major challenge for peptides.
Duly noted. A high-impact candidate with a delivery hurdle. Okay, let's wrap up with our final paper. A highly scalable agent targeting chronic inflammation and cellular senescence.
This is our final paper, published November 7th in Aging Cell by Nia Pattison-Rees and the University of Birmingham team. It introduces us to butyrate.
The microbiota-derived short-chain fatty acid, and they define it not as a senolytic drug that kills senescent cells,
but as a xenomorphic agent. And this is a really crucial distinction. It's a new way of thinking about senescence.
So what does a xenomorphic do?
It essentially suppresses the induction of senescence in the first place, and it blunts the pro-inflammatory SASP.
The senescence-associated secretory phenotype. that toxic cocktail of molecules like IL-6 and IL-8 that drives inflammaging.
Butyrate just suppresses the release of that cocktail. The mechanism links your gut microbiota directly to immune aging and systemic inflammation.
And it does this through the GPR109A receptor, which inhibits MTR, and that in turn suppresses NF-kappa B.
Which is the master regulator of inflammation. So by targeting it with a simple gut metabolite, they showed a profound effect. And the proof of concept was fascinating.
What was it?
They showed that fecal supernatants from young butyrate-rich mice could effectively reverse aged splenic senescence in vivo.
That microbiota immune axis data is so compelling. It really highlights how much of systemic aging is driven by what's happening in the gut.
And butyrate is easily the most scalable therapeutic we've discussed today. It's cheap, maybe $10 a month, and can be delivered as a dietary intervention.
Which makes combination studies the critical next step.
Absolutely. Can butyrate, by acting as a xenomorphic and anti-inflammatory, improve the efficacy or maybe the safety profile of a traditional senolytic like dasatinib and quercetin? We need to find out.
So let's pull this all together. 5 fascinating agents hitting 4 different hallmarks this week. Telomere maintenance with SERCR1.
Epigenetic stability with HDAC2 and Cadmium-5A, mitochondrial health with SS31.
And chronic inflammation and senescence with butyrate. So what does this all mean when we put it together?
It just solidifies the idea that true breakthroughs in longevity, the kind that add 10-plus healthy years, are going to require combination therapy. We're now fundamentally moving into the era of epistasis studies.
Analyzing how these mechanisms interact in complex, nonlinear ways.
We have to design trials to understand synergy. What happens if you stack a telomerase activator like SERCR1 with an epigenetic corrector like an HDAC2 inhibitor and a xenomorphic like butyrate that suppresses the core anabolic pathway, MTUR?
That's the crucial next step for biotech. Designing those combination trials to look for synergy before safety issues pop up in humans.
We're moving toward polypharmacy in longevity. And that brings us to the final provocative thought we want to leave you with today.
It centers on the biggest tension we identified. Considering SERCR1 provides systemic rejuvenation, but also carries a potential cancer risk.
And butyrate inhibits inflammation, but also MTO, a core pathway for cellular growth.
What is the greatest theoretical danger in stacking those 2 specific agents? And how do our preclinical models have to change to anticipate that specific antagonistic risk?
Balancing that drive for proliferation with the need for systemic anti-inflammation. That is the ultimate tightrope walk in longevity research.
And that tension is where the real complexity and the biggest opportunity lies. Thank you for joining us for this in-depth look at the longevity papers.
We invite you to continue that critical conversation. Until next time.